Good afternoon, everyone. Thank you very much for coming. It's Monday. It's not our usual day, but we have a special guest, so we decided to have another seminar today. So we have Kaining Ding from Juelich. I hope that I said that correctly. I always feel that I don't say that well. So I assume that a lot of you heard about Kaining. He led the last year Heterojunction workshop that was very successful, and I think that we have another one this year.
Yes.
That's the plan. Kaining did his undergrad and master in Aachen. I hope again that I said that correctly. And then a PhD in Juelich that he is team leader there. His expertise is from material science, so he works a lot with silicon and silicon alloy. But now with the group, his interest is mainly on the heterojunction solar cells, passivated contact, but also, like you say, and in this presentation, I think it will be also about some kind of application of PV, mainly for vehicles. So, Kaining, it's great to have you first time here at UNSW. I hope that you will enjoy the visit, and we're looking forward to hear what you have.
Awesome. Yeah, thank you, Ziv, for the organization and for the agenda of today. So hi everyone. So my name is Kaining Ding. I'm from Research Center Yulish. So it's my first time to Australia. I come from. I knew that Australia is far away, but after taking the flight myself, I knew it's really far away. So next time I meet any of you on a conference in Europe, you will have my personal apologies for the long trip. Anyway, but very nice country. I have seen quite some nice spots of Australia so far. So this is going to be more overview talk about the Research Center Yulish and our crystalline silicon PV activities, but also introducing the institute. So let me start with this graph. I personally like it very much because for those of you who are not familiar with the German research infrastructure, this is actually a good one. So here you have a plot that shows the intensity, or as well as the money spent on research. On the y-axis, on the x-axis is the time scale of the usability of the research people do. Yeah, and on the one hand, you see there is an industry that works, of course, very closely to application-oriented research. And you see a lot of universities. So this just means the university in Germany, the institutes at the university, the professors, they often decide what they want to do. So they can go more application-oriented, or they can go more curiosity-driven research. So this totally depends on them. And there is also Fraunhofer. So many of you know Fraunhofer ISE. So that is the industry application-oriented research organization in Germany. So they work very closely with the industry, and most of the money they get will come also from the industry directly. And there's also, here you might not see it, so Max Planck. So this is an organization that works on more curiosity, basic research, not really attached to any application. And there is also Helmholtz. So there is an association that basically deals with everything from application-oriented to curiosity-driven, but not in everything. So the Helmholtz is a federal government association directly paid by the government, working on, they call it grand social challenges, so like energy problems or health. So these are the grand challenges that people need to work on. And also you need kind of an association that can also work on application-oriented topics without actual interest of the industry in the moment. So to have a better lifespan of topics. So that is how it looks like. So, and the Research Center Juelich is part of the Helmholtz. So the research center Juelich, it's located in a town, in a very small town called Julish, in the most western part of Germany. So, so I try to find the mouse. No. So here, yeah, Forschungszentrum Julich, and so I have checked. So Julich has an inhabitant of like 30,000. So it's a really small town, and I think the bigger cities close by are Cologne and Düsseldorf. You might know them, and it's right at the border to Belgium and the Netherlands. It's actually one of the biggest research centers in Europe, with over 6,000 employees in the moment. And the research areas are energy and climate, information and brain, and some key technologies. So this means supercomputer or the most modern electron microscope and so on. So this is kind of a big infrastructure. So the Institute for Photovoltaics, it is part of the energy and climate. And this is an institute that is only working on photovoltaics. We have around 100 people, and in the moment there are 6 research groups. So one of them is working on organics and perovskite solar cells, mainly with a focus on with a focus on analytics. And there's also a group working on the module analytics, and another one specializing in laser processing, as well as some activities on the application of silicon thin film solar cells. So we use silicon thin film solar cells to drive electrochemical reactions, so like splitting of water or charging of batteries or the reduction of CO2. And last but not least, there is a group concentrated on crystalline silicon activities. So this is where I come from, so therefore I will now concentrate on that part. So we actually, the research center Julich was once known for silicon thin film solar cell, especially the fabrication of micromorph tandem solar cells. So here you can see on the left, so this is kind of a simple sketch of a silicon tandem solar cell with amorphous silicon bottom and microcrystalline silicon top cell and bottom cell. So this technology was once, you know, when the price of the wafers were very high. So this technology was, many people consider is as a future. And also there was actively industry for silicon thin film solar cell, but with the price reduction of the wafers for crystalline silicon, so this industry actually went out and vanished. So we also had to think about new products to work on at the institutes. So basically we know a lot of thin film know-how. And this we try to use them on silicon heterojunction solar cell. Basically, a lot of films you can transfer directly from silicon thin film to silicon heterojunction solar cell. I think many of the companies and research institutes that were working on silicon thin film so went the same way. I think the expertise are silicon alloys and TCO films, and particularly the know-how of making multi-junction cells, light management and laser processing. So the key expertise is application of novel materials and processes in heterojunction solar cells. This is what we do. So formerly we were the silicon heterojunction group, but now in the moment we expanded our activities a little bit more. But our main mission as a main collaborator for crystalline silicon activities at the Institute is to establish a baseline for the industrial-sized M2 heterojunction solar cells. And what we are working on right now is to establish a baseline for the silicon solar modules for vehicle integrated PV in particular. And also establish a process and characterization standard for passivated contact solar cell. And from the material scientific point of view, what we think is our expertise is the application of silicon alloys and hot wire CVD processes in heterojunction solar cells. So I will shortly give some examples. First of all, the heterojunction solar cell in the baseline. We have been working on many different types of front emitter and rear emitter, or even IBC, but by the end we decided to focus on the rear emitter, so which means that we have an N-type wafer, and the P layer is on the back side, and the front side is an N-type front surface field. The reason to choose that is that according to the experience is the doped material. It is easier to make N-type doped thin film material than a P-type one. And we are also working extensively on N-type microcrystalline silicon oxide or microcrystalline silicon. So therefore we decided to put it on the front side. And also we concentrate on the industrial size, because I think this is where heterojunction is going into the mass production. In addition, so we are working on different kinds of alternative TCOs, and also elaborate the smart wire technology. And the special focus we have with another team working on it is heterojunction on very thin wafers. So not from a process technology point of view, but from the physical understanding point of view, to try to understand where are the limits if you use thin wafers. And also, together with another group, we are working on perovskite silicon tandem. So this silicon heterojunction baseline that we have built up. It's still from the process-wise, it's still on the ramp up, but so far it has been finished. So we have the wafer pre-treatment, and it's basically a ozone-based cleaning. And the texturing is conventionally with KOH. And the silicon deposition, so it's on the Meyer-Burger PCVD platform. It has 3 chambers for 9 M2 wafers each batch. And with the TCO in the moment, this is a system from Ardenne. But also we will get another one also from Meyer-Burger on the Maya platform with higher throughput. So this is where we do the TCO. And the screen printing is done on the Microtech system. It's a company from Japan. And also we have the Luana. So I've seen Luana here, so it's speeding up right now. But the one we have is a combination of a PV2's equipment plus a LED source of wave labs, so that you can also do LED EQE using that. So as I said, so the silicon heterojunction baseline we have is a mandatory step. Because we have to demonstrate high efficiency on the industrial relevant processes before we can apply our innovative materials and processes. And I think in order to improve the efficiency further, it's important to do many cells. I think we are talking about incremental improvements from now on. In the moment, the efficiency is somewhere above 21, but I think by the end of this year we are targeting above 22, even maybe 23 by the end of this year. So the aim of why we are doing it is to test our materials and processes targeting efficiencies larger than 25%. So here I want to introduce you two materials in particular that we work on. One is the nanocrystalline silicon oxide. So it is a material deposited by plasma enhanced chemical vapor deposition. It is it gets its final form after the deposition, so there is no additional annealing treatment or so. And this material consists of silicon nanocrystallites of 10 to 20 nanometers that are connected in a three-dimensional network. So what you can see is maybe here illustrated in blue. And it's surrounded by amorphous silicon oxide. So basically the way how you do these materials, you introduce CO2 and silane and the doping gas and hydrogen. Basically with a good, very high dilution with hydrogen, you can get this kind of as-grown material. And so this kind of a network formed by the nanocrystalline silicon, so these red dots here are in this case are phosphorus dopants. So they can give you the conductivity in the vertical direction that you need for your cell. But this amorphous silicon oxide, so they give you additional transparency. So this material, microcrystalline silicon oxide, you can see it from here, the dark conductivity plotted versus optical band gap. So if you have intrinsic amorphous silicon, doped ones, they are mainly here around this area. So you can see by using this microcrystalline silicon oxide, you can have a better compromise between optics and electronics. Yeah, depending on how much oxygen you add to the process, let's say. So this material has been found its way into the mass production in silicon thin film solar cell as an intermediate reflector. But for silicon heterojunction solar cell, I think many companies have tested it already. I think the major issue is with the deposition rate. So you have to use a very high hydrogen dilution to make this crystalline structure. But with the increase of the hydrogen dilution, you also decrease your deposition rate. You can find ways to increase the deposition rate. So actually, for example, by increasing the power, but again, you will get more problems with powder formation in the system. So so in the moment, it's still a material that is being tested by companies in the production, but I don't think it is a standard in the moment. Also, here what you can see is uniformity of this material in the Meyer-Burger system. So these are the 9 positions of the wafers, and we plot the E04 of the films measured at this position, so at the edge of the chamber and also in the central part of the chamber. You can see quite good correlation. So which means that what I don't show is the thickness. So the thickness is also very homogeneous, and also the optoelectronic properties are quite okay. The reason why I'm showing this is that we basically have a focus of our cell development for the integration into the automobile industry. So this is our 2 projects in the moment we have. One is with Audi and one with a company called Street Scooter. The Street Scooter, I think maybe people from Germany might know them. It's a company owned by the German Post. So these kind of cars are fully electric, and they have this kind of cabin. People use it to deliver post or packages. Okay, so so one of the ideas is to put the solar modules on roof and on the side of these vehicles, and to try to extend the range of the driving without recharging. And the project here with Audi is to put the heterojunction modules on the car roof. In this case, it's not an electric vehicle, so and the power supplied by PV is only for auxiliary charging. So with this special application, so the aesthetic become really important. and also the difference in the optics is really crucial. So basically you need to have solar cells independently from which angle you look at them, and independent from the intensity of the illumination, they should look similar. So they should look exactly the same. So if you think about silicon heterojunction, so this means all the films have to be exactly on the one wafer. They have to have this exact same thickness in order to have the same optics. And also another challenge of the integration of heterojunction solar cells into vehicle is, in this case, it's not a big problem, but here you have a curved surfaces. So how to integrate the PV into curved surfaces with using crystalline silicon solar cells is still challenging. I mean, there are a lot of cars out there with PV, crystalline silicon PV on roof, but you will also all see that they do not cover the whole roof, because to the edge of the roof the curvature gets more severe. So this is often where people start to neglect, to not put the PV there. So usually the PV is a little bit smaller than the whole roof. Okay, so that's about nanocrystalline silicon oxide. So the next material that I want to introduce is the microcrystalline silicon carbide. So I think this is we call it our magic material. Yeah. So if this is grown by hot wire CVD, so you basically dissociate your precursor gases at a hot wire up to 1800 or 2000 degrees C, and the dissociated radicals, they come to the surface and form a film. Here is cross section of microcrystalline silicon carbide. You can see this silicon carbide has a stoichiometry about 1:1, so it's like 50% silicon and 50% carbon, and they form this kind of crystallites. So basically this is a material consisting of crystalline silicon carbide phase and amorphous silicon carbide phase, so very different than the microcrystalline silicon oxide. And the crystalline volume is both responsible for the conductivity and for the optics. So you would like to have it as crystalline as possible. There is no active doping when you do this process. The doping, we believe, come from nitrogen and oxygen as a residual in the gas chamber. We also worked on the active introduction of nitrogen and oxygen into the process. Seems also to work. So up to now, the general understanding is if you want to make this material highly doped, you need to have a certain level of nitrogen. These are the dopants. This generates electrons in the silicon carbide, but also you need the oxygen. The oxygen, they do not increase the charge carrier density, but they increase the mobility. So we believe that it's connected to the reduction of mobility boundary at the interface of the grains if we implement oxygen at the interface. But this material here you can see. I think the microcrystalline silicon carbide, if you compare it with a microcrystalline silicon oxide or even amorphous silicon and microcrystalline silicon, it has far the better compromise between optics and electronics. But there is also a big problem with this process, is that there are a lot of hydrogen radicals generated during this process, and they usually etch away everything that is beneath. In particularly, we tried to implement into a heterojunction solar cell, but there was no chance for the amorphous silicon passivation to survive this. Therefore, we started to work on silicon oxide passivation. So it's a wet chemical silicon oxide in this case. similar like in the passivated contact solar cell, with relatively good results in lifetime. It's important to mention that this lifetime is achieved directly after the deposition. So you deposit a wet chemical SiO2. You can use actually many methods to do that. And then you grow a microcrystalline silicon carbide on top of it. And without any further treatment, so no post-annealing and no hydrogenation afterwards. So you can get IVUC up to 730 millivolt. What we have been working on as a device is to implement this contact, so microcrystalline silicon carbide and silicon oxide on the front side of the cell, and on the back side it's heterojunction rear side. This is used just simply because this is what we can do best. But I think in future it would make more sense to make also passivated contact on the back side. Without the TCOs, I think this would be a very competitive two-side contacted solar cell device as compared to the silicon heterojunction. Okay, so these are some preliminary cell results. We have got what is shown here is the results of this solar cell shown here, and also that of a reference. So reference means a standard heterojunction solar cell rear emitter. So in this case, the reference was not very good as well, so I apologize for that. This is obviously having some issues with the fifth factor. But what you can see here is that we have loss of VUC. And this is mainly due to the sputtering process of the TCO. But I think this is a very general problem with passivated contact. Even if you have polysilicon SiO2 contact and you deposit a TCO on top of it, the same thing will happen as well. Up to now, I have no idea why this is happening. So we have ruled out that it is the ion bombardment, because microcrystalline silicon carbide is one of the hardest material we can do. And also we have tested the UV, so whether the UV from the sputtering process is affecting the passivation. So namely the hydrogen at the interface between crystalline silicon and SiO2. Also, that does not seem to be the case. So I think here it's still an open research question why it is happening. But nevertheless, what you can see is that the current as compared to our reference is much higher. So I think if the reference would be like the 21 or 22% level, I think the JAC should be able to come above 40 milliamps. So, but nevertheless, so I think this is the first low temperature transparent passivated contact we have ever done. Also talking about passivated contact, as I said, I think the ultimate device would be a passivated contact on the front and on the back. So therefore we also started to work on the back side using SiO2 polysilicon. But here again, we concentrate on what we can do best, namely with a hot wire CVD. So first of all, we grow a 1.5 nanometer ton oxide. And then we use hot wire CVD to dope to make a amorphous silicon film. But also we can do silicon oxide and silicon carbide with it. And then after the furnace annealing, it will turn into polysilicon. And then we deposit silicon nitride and do the screen printing and do the firing. That is the plan. So currently, the best IVUC is also around 730 millivolt with this stack. but the deposition rate, which is let's say the beauty of a hot wire CVD, it can go up to 42 nanometer per minute. So as I said, there are a lot of things to be understand for passivated contact solar cell, especially if we can have the possibilities now to compare the standard, the conventional SiO2 polysilicon and the microcrystalline silicon carbide SiO2 contact. I mean, there are a lot of difference, but also similarities. One of them is, as I said, the drop of the VOC after TCU sputtering. So why is this happening? And important to note that this kind of problem don't seem to appear with heterojunction, or at least the sputtering damage can be recovered. And with a passivated contact, it seems to be more difficult. And also, what is the difference is we have with a microcrystalline silicon carbide, we have a low temperature process, which means the silicon oxide, tunnel oxide, does not see any high temperatures during its processing. So so it cannot have. I mean, for the polysilicon SiO2, usually people believe that the high temperature is also important for the reorganization of the SiO2 at the interface, which is very obviously not the case with microcrystalline silicon carbide. And also there is no diffusion of dopants into the crystalline silicon, because there's also no high temperature. And for the polysilicon, the profile of the doping into the crystalline silicon seems to be important, but with the microcrystalline silicon carbide, it seems to be not less important, so you can have a good passivation also without that. I think using these two different comparisons, one could learn a little bit more about the mechanisms of how it works. What I want to show here is that this is a system we built up recently. It took us 5 years. It's a cluster consisting of a deposition system on the one side with many different techniques. And on the other side, you have surface sensitive characterization techniques. And what you could do is to, after deposition without a vacuum break, you can transfer the samples through here. So to the characterization systems. And we hope to be able to use that to analyze more things. For example, the composition of the materials at the direct interface using XPS, UPS, but also the crystalline structure of the materials using LEAM or PEAM. And for example, conductive AFM can be used to detect ping holes on the surfaces, and so on and so forth. So I will come to my summary. So I think the most important message for my presence here is that Research Center Juelich is working on heterojunction and on passivated contact. And the expertise is the thin film materials and processes for heterojunction solar cells. And in particular for heterojunction, we are working on more industrial sized processes. And the scientific or material scientific expertise, the silicon alloy materials, and also hot wire CVD processes. So that's it. Thank you for your attention. So I switched only a little bit on the surface, so if there are questions, I would be more than happy to answer them.
Any questions?
Hi, yeah, thank you very much for your talk. You mentioned earlier, towards the start, you were talking about the heterojunction cells on very thin wafers, down to like 40 microns.
Yes.
Can you tell us a little bit about that process and about the yield that you have making those cells?
So it's also, yes, so as I mentioned, we're not, on that topic, we're not working on process technology. I know the yield is quite low, so there are a lot of breakages during the processing, especially between 40 and 80, so you have the valley of death for the wafers. But with the manual processing, so we are not talking about machines selecting the wafers. People can learn how to deal with them. So the breakage rate in the moment is quite low, but in the beginning it was maybe every second wafer. So is that the question, or?
Yeah, just yeah. So I mean, when you're moving to an industrial setting, though, you have the vacuum tools to move the wafers around.
Mm-hmm.
So you haven't been doing that with the.
No. I'm not sure. I mean, the industry is going to thinner wafers, but not that extreme. So I think they don't consider wafer thicknesses below 80, or even maybe 100. And I don't know how, and I think there is no idea how to deal with them like that. But the question here is to see. I mean, on the one hand, you can do simulations to tell if I reduce the thicknesses, what will happen with the JSC, with VOC, with the passivation. But what we would like to do is to also on the experimental side to do that and see what are the effects coming. Maybe there is something that simulation does not consider.
Do you have really poor long wavelength response with the thin wafers?
Sorry?
The long wavelength response, is it really poor with the thin wafers because they're so thin?
The long wafer response?
Yeah, so...
Long wavelength.
Yeah,
okay,
the EQE at long
Yeah.
wavelengths, is it very poor because the wafers are very thin?
Yeah, it is.
Other questions?
Yeah, so you talked about the hot wire CVD system having a very high deposition rate.
Yes.
Do you see it as a genuine competitor to PECVD for these types of devices, for industrialization?
Yeah, it is. I mean, the hot wire CVD has advantages and has drawbacks. So from an industrial point of view, I mean, the advantage is on the one hand the deposition rate, high deposition rate you can reach, and on the second hand the absence of plasma. But the drawback is for sure that the wire lifetime. So if you are making silicon, the wires will silicide during the process, and at some point they will break. I think there is only one company. I mean, I'm talking about PV. Okay, so in the PV, for heterojunction in particular, there is only one company, IVAC in Japan. So they sell hot wire CVD machines, and they usually promise uptime of 2 weeks before they have to change the wires. But also the changing of the wires is something that can be optimized. Usually you can take out all the electrode, including the hot wire, and place a new one. In Europe, it's not a big discussion about hot wire CVD for PV, so I don't know why. But in China, there are a couple of companies having pilots in the volume of 100, 200 megawatt, using hot wire CVD and to do intrinsic and doped amorphous silicon, and the results are actually quite good. But I think there are certain limitations in the throughput, because you have to deposit everything on the vertical, because you cannot span meters of wires in the horizontal, so you let the wires hang probably, and therefore you have to deposit in the vertical. This means during the mounting, you have to mount all the wafers, and you have to cover them with a mask or a holder and put it vertical, and then so it takes time.
What about the energy consumption of that machine? Because you're going to very high temperatures. You're avoiding the plasma and the ion surface bombardment without the plasma. But then you're going to very high temperatures. Is that actually feasible for?
I mean, I'm not sure about that point, but I mean, you are only heating up the wires. Yeah, I don't think it's too different than PECVD. Yeah, I mean, you are not heating up the
wafer, the substrate itself. Yeah.
I mean the substrates, they have a substrate temperature, and this is maybe kept by 100 or 200 degrees C, and the wires they will increase the temperature on the substrate a little bit, like 50 or 100 degrees C. Yeah, but you don't heat up everything up to this high temperature.
Is it basically evaporation? What you're doing with that? So it's just a wire.
It's a debate. Yeah. So therefore, I think there are two names for hot wire CVD. One, people call it hot wire CVD. Yeah. And other people, especially people in Japan, call it catalytic CVD. Yeah. So I think it's a matter of operation range. So if you are operating at temperatures like 1,400 and a little bit below or above, you are talking about catalytic effects. Yeah. So it's not only a thermal dissociation of your precursor at the surface, but also some chemical effects. You know. So it's a catalytic effect. But if you go to very high temperature, like 1,800 and 2,000, maybe it's purely the thermal, the temperature that doing the job. Yeah, so it depends.
Other questions? It's great timing because we're hoping to go as well. So let's thank Kaining again. Thank you very much.
Okay, thank you very much.